Alright, welcome. We're going to be doing a 3.4, 3.5 today, so we'll combine them. We'll try and go as quick as possible. Okay, so 3.4 right here is parallel lines. Remember, parallel lines never touch. And we are going to have perpendicular lines, lines that come together to make 90 degrees. So we're going to relate them together. So make sure you have 3.4 at the top here. And our first thing that we're going to have is you're going to write down this theorem. So make sure when you're writing this down, you write down everything that's in the box. You're going to write down the example right there, and then it should look very similar. This will be a good way to help you study. Okay. So theorem 3.8 says if two lines are parallel to the same line, then they are parallel to each other. So you see how these are a conditional statement. It's an if-then statement. So we should be really good at conditional statements right now. Okay. So it's saying right here that if A, B are parallel, and you see how we have the arrows right there showing that A, B are parallel, and if B, C are parallel, see how we have the two arrows showing that both B and C are parallel, then that must mean that A and C are also parallel. Okay, so this is a theorem. Remember the difference between a theorem and a postulate. A postulate, it's a given truth. A theorem is something that we can prove. We do a two-column proof, and we could prove that this is true. And when we're looking at this, when we kind of look at the logic behind this, this is kind of like our transitive property. Like if A and B and C, then A and C must be also parallel. So it's very similar to our transitive property. Okay. Alright, the next one that I'm going to write is theorem 3.9. So we're going to write down everything inside this box right here. So theorem 3.9 is in a plane, if two lines are perpendicular, meaning that they come and make 90 degrees, to the same line, then they are parallel to each other. Okay. So when we're writing this, M is perpendicular, and that right there is the sign that we use for perpendicular, like an upside down T right there. So if M, let's erase that right there, if M is perpendicular to T and N is perpendicular to T as well, then line M and N must be parallel. Remember, that's how we write parallel right there. Okay, so this is a theorem. Remember, a theorem is something that we could prove. So when we're looking at this, we see that when they make when M and T make a perpendicular line, they make 90 degrees. N and T also make 90 degrees right here. So remember, those two angles are corresponding angles. When corresponding angles are equal to each other, remember the last lesson that we had, 3.3, we use our converse theorem of corresponding theorem right there, which is saying that if the two angles are congruent and they are corresponding, then that must be that line M and N are parallel to each other. Remember, that's what we just did. Okay? Alright, on to the next one. Alright, so our last theorem that we're going to write down is theorem 3.10, perpendicular transversal theorem. So in a plane, so a plane is like a surface. So it's like, think about like our classroom, like the floor would be a plane. The ceiling would be another plane. Those are two separate planes. Okay? So in a plane, if a line is perpendicular to one or two parallel lines, then it is also perpendicular to the other. Okay, so in this example that we have, which you're going to write down, if N is perpendicular to L, and they make a right angle right here, and L and M are parallel lines, then that must mean that these two angles are corresponding angles. If they are corresponding angles, it means that they are congruent, which means if that is 90 degrees, that one needs to be 90 degrees, which means that N would make a perpendicular angle with T. Okay, perfect. Alright, so we got a few examples to do. Alright, so we got our first proof right here. Okay, so we're going to label it problem number 1 at the top. Problem number 1. Alright, so given right here is in a plane C is perpendicular to B, B is perpendicular to D, and D is perpendicular to A. So what we are trying to prove that C is perpendicular to A. Alright, so when we're doing the proofs, we want to first just kind of think what's going on here. Okay, so we have all of these right here perpendicular to each other. What we're trying to prove is if this line, as an arrow keeps going, we are trying to prove that C and A make a perpendicular angle. So we're trying to prove that right there, okay? So we got to think, how can we prove that? So let's do our two-column proofs. So let's do statement and our reason over here. Reason. Alright, so a two-column proof. Alright, so first thing should be easy. We should write always what's given to us. So we're going to say C is perpendicular to B. B is perpendicular to D. And D is perpendicular to A. And what we should do is we should always label these. So let's label this as 1, circle it, and over here is 1, so we know exactly what matches up. So what's the reason? That was given. Alright, now number 2. Okay, so we got to think. With our new theorems that we use, and we can use those now, what are we trying, how can we prove that those two lines make a perpendicular? Well, we can kind of see it, right? We can imagine that obviously if that's perpendicular, they're all going to be perpendicular, okay? But how can we prove that, okay? We first need to prove that C and D, these two lines, are parallel. Because if we can prove that those are parallel lines, these two angles are both in corresponding spots. If they are parallel lines, corresponding angles are congruent. So if that's going to be 90 degrees, the corresponding spot has to be 90 degrees. So we just have to prove now that that angle is going to be, that the two lines are parallel. So how do we prove that? Okay. Well, we see right here that this angle right here and that angle, both of those angles are perpendicular, which means that they are congruent, that they are the same. So we're going to use the second theorem that we listed right there. So we know that C is going to be parallel to D. So we're going to write C is going to be parallel to D. And how do we know that? So usually with our theorems, if we just have a name, we can write our name down for the theorem, but this one we don't, so we kind of have to write out what's going on. So we have to write out kind of what we wrote up before. We say if two lines are perpendicular to the same line, then they are parallel. Alright, so because C and D are both perpendicular, then they are going to be parallel lines. Okay, so from here, whoops, I have this right here. Okay, so we know that these two are now parallel lines. So because we know that they are parallel lines, these two are both in corresponding spots, which means that they have to be congruent. So this was like our last theorem that we had, where this was our, remember our 3 dash in our book right here, our 3-10 right there. That would be our transversal, perpendicular transversal theorem. So we are going to write step number 3, that C is going to be perpendicular to A. And how do we know that? 3, because perpendicular transversal. And we'll just abbreviate theorem. Remember, our perpendicular transversal theorem was that in a plane, if a line is perpendicular to one or one of two parallel lines, and it also is perpendicular to the other. So what that means though is that this one is perpendicular. These two lines are both parallel, so this other angle also has to be perpendicular. So it's really important that you remember these theorems, because we're going to have to use these theorems in our proofs though. So like to do the proofs will get a little bit hard if you don't know the theorems. So you got to make sure we know the theorems. So whether you need to make flashcards or drill and kill or a vocab thing, whatever it is, you got to remember what the theorems are. Okay. All right. So that's our last problem for 3.4. So we're going to do 3.5 pretty quick right here. All right. So our next one, we're going to jam this one through pretty quick too. All right. So we're going to do like another page, 3.5, parallel lines and triangles. So we're going to use our parallel lines to prove a theorem about triangles and to find the measures of triangles as well. Okay, so make sure you have that title at the top. Alright, so our first postulate, so remember a postulate is something that we're given to be true, is, we're going to write down this whole box, right, parallel postulate at the top. Everything in the box, including the picture, we're going to say through a point, not on a line, there is only one and only one parallel line given to a line. So there is exactly one line through P parallel to L. Okay, so all that's saying though is that if we have one line going through a point, that another line right here would also be parallel, because if I drew another line and it looks something like this, these two lines would like eventually cross. Remember, parallel lines are lines that never cross. Okay? Alright, on to our next one. Alright, our next theorem is we're going to have a triangle angle sum theorem. So everything inside this box. So the sum of the measures of the angles of a triangle is 180 degrees. So you should probably remember this from previous grades, that if we take each of these angles right here, A, B, and C, and if we add them all together, we're going to get, yes, you guessed it, 180 degrees. So it doesn't matter what type of triangle, as long as it has three sides right there, those three will add up to 180 degrees. Perfect. Alright, for our next one, we have a couple vocab. So you're going to write down this picture right here, this little paragraph, and these three pictures. So it says that an exterior angle of a polygon. Remember, interior is like inside, exterior is outside. So on the outside angle of a polygon, an exterior angle of a polygon is an angle formed by a side and extension of an adjacent side. So if we're looking at like these three pictures right here, we see that this angle 1 in each three of these pictures is on like the outside of the polygon, of the triangle. So that's exterior, it's on the outside. So for each exterior angles of a triangle, the two non-adjacent interior angles are its what we call remote interior angles. Okay, so like when you're thinking like at a remote, so if we are sitting at home and we have our remote and we're trying to change the channel on that, we're like usually not right next to the TV, right? We're not next to it pushing the buttons. We're like at a distance. You know, we're at a distance. So it's the same thing here. If we look at angles 2 and 3, they aren't adjacent to one. They're not right next to each other. They're far away. So they are at a distance from angle number 1. So that's what remote means. You're kind of like at a distance. Think about like a TV. You're not right up next to the screen. You're at a distance right there. Same thing with angles 2 and 3. We look at each of these pictures. They are not adjacent to one, but they are at a distance. So we're going to use that knowledge in order for our next theorem. Alright, so our last theorem that we're going to write down, so we're going to write down this box. So make sure that you label it, saying triangle exterior angle theorem. So the measure of each exterior angle of a triangle equals the sum of the measures of its two remote angles. So angle 1 right here is going to equal 2 plus 3. So angle 2 and angle 3 is going to equal what angle 1 is. Okay? So it's a theorem. We can prove what it is. So it probably has a relationship to 180 degrees. But we need to know that this angle right here, 1, is the same thing as 2 plus 3. Okay? Alright, so let's go into some problems. Alright, so our problem number 1 that we're going to have right here, we're going to write problem number 1. You're going to write the picture, and our instructions are to find x, y, and z. Alright, so we have these two triangles right next to each other, and we got to find the missing angles, x, y, and z. Okay, so if I'm looking at this one, I see I have a triangle right here, and remember our theorem that each side of the triangle needs to add, the whole triangle needs to add up to 180 degrees. So if I'm trying to find this one, and I know that one angle is 80, and I know that this other angle is 30, and if I don't know what this angle is, let's say it's x, we know that's going to equal 180 degrees. So this is going to be 110 plus x equals 180, which means that x is going to equal 70 degrees. So right here we have, this is going to be now 70 degrees. Okay, so I'm looking at this, I'm trying to figure out what y is now, but I see x and y are a linear pair, which means that together, when I put them together, they make a straight line. So if this is 70 degrees and it makes a straight line, which is 180 degrees, that means that y needs to be 110 degrees. So this needs to be 110 degrees. So let's put over here. We have x, which is 70. We have y, which is 110 degrees. Now we got to find this last one. Okay, so we have z. Again, we have this triangle now on the right there. And we have three angles. We know that each three of the angles are going to add up to 180 degrees. So this top angle right here is 40. So we're going to write 40. The bottom one we just found, which was 110. 110. And we don't know this last angle, so that is z. Let's make sure it doesn't look like a 2. So that's z right there. And we know that when we add these three angles together, it's going to equal 180 degrees. So I add these two together, I get 150 plus z, not a 2, is going to equal 180 degrees. Subtract 150 from both sides, and I get z equals 30 degrees. Z equals 30 degrees. Perfect. So with that problem, I just got to remember that triangles, the three sides of the triangle add up to 180 degrees. Very important. Okay, next one. Alright, my problem number 2 right here. We're going to write problem number 2. This one should be nice and easy. Problem number 2. Alright, so there's two ways to solve this. So if we can remember our theorems, it's a lot easier to solve it. So if we remember our theorems that the two remote angles are going to be, when you add them together, they're going to equal the same as the exterior angle. Okay, so how can we prove that though? Okay, let's say we forgot that. Well, we know that a triangle right here, each three of the angles added together, 80 plus 18 plus that missing one x, is going to equal 180 degrees. So this is 98 plus x equals 180. So x is going to equal 180 minus 98 is 82. Alright, so this is going to be 82 right here. That's 82 degrees. And if these two are a linear pair right there, we know that they add up to 180, so 180 minus 82 is going to be 98 degrees. 98 degrees. So that's what angle 1 is right there. 98 degrees. But look, we have all this work right here, all this work, but that theorem that we memorized can save us a lot of time, because all we had to do was just take the two angles right here that aren't adjacent to the exterior angle and then add them up. If I just took 80 plus 18, that gives me 98. A lot quicker and a lot easier than having to go through the whole process right here in order to figure out what that exterior angle is though. So if you take the two and you add them up, they're going to equal that one. Okay? Alright, last one. Alright, so we're actually just going to leave it off right there. So that'll be our last problem. Thanks for staying tuned. We'll go over more examples in class. Alright, see you guys.